Good day. The topic is braced cuts. So for braced cuts, the excavation supported by proper bracing system. And some purposes are, first, construction of foundations, and the other is construction of utilities such as sewers. Okay, so an example is, so we have therefore in image, so our sectional view and for our strut system. So for the pressure variations for the design of these brace excavation or brace cuts, so we have three. First is under sand. So for the pressure now, the sigma A prime is equal to, or the sigma A rather, is equal to 0.65 Ka times gamma times height, wherein Ka is equal to 1 minus sine of phi prime all over 1 plus sine of phi prime. Next, for the case of soft to medium clay, so this sigma A is equal to Ka times gamma times H, wherein Ka for this condition, gamma all over H over Cu that's greater than 4, Ka is 1 minus 4 times Cu all over gamma times H. And for our last, the stiff clay, that is for gamma H all over Cu that is less than or equal to 4. So the Ka is 0.2 to about 0.4. So what is this Cu? Again, that is your undrained cohesion or undrained shear strength. So let's apply those three with our example. So for problem 14.9 in page 575. So the elevation and plan of a bracing system for an open cut in sand are shown in figure 1.7b. So using PEC's empirical pressure diagrams, so determine the design strut loads. So given the saturated or the gamma of the sand rather, is equal to 18 kilonewtons per cubic meter. So phi prime is 32 degrees. X is 1.83 meter, Z is 0.91 meter, and the strut spacing is 3.05 meter. For our requirement, so strut loads at level A, B, C, and D. Okay, so for our solution, so again, this is under the sand condition. So for our lateral earth pressure, we need first to determine what is the total height H. So H, as based on the diagram, is equal to Z plus the summation of different X. So Z, which is 0.91 plus, we have 4 of X, that is 1.83. Thus, H is equal to 8.23 meters. So determine now the lateral earth pressure for sand, in which our sigma A is equal to 0.65 of Ka times gamma times H. Wherein, we have therefore 0.65 times the quantity 1 minus sine of phi prime, which is 32, all over 1 plus sine of 32 degrees, times the value of gamma of this sand, 18 kilonewtons per cubic meter, and multiplied to the total height, that is 8.23 meters. Sigma A, that is uniformly distributed, is equal to 29.586 kilopascals. Okay, so with these 29.586 kilopascals, towards now the sheet bracing, so let us therefore assume that hinge connections at the different levels. So for our levels A, B, C, and D. And we need to divide into sections so that the assessment is similar to analysis of simply supported beams. So we need to consider two different points or levels, so for us to analyze what are the different line loads. Okay, so therefore for this problem we have section 1 for AB, section 2 for BC, and section 3 for C to D, and so on. Okay, so for section 1, since we are exposing only A and B, and since B is exposed to section 1 and section 2, we will be having two values of B. For this section 1, this will be B sub 1. Okay, so for us to analyze the values of our A and B1, so we need to work on our equilibrium equation. So if we will employ the summation of forces horizontal, it is not possible since we have two unknowns. So unknowns A and B prime. Therefore, so to eliminate one unknown, so we need to apply summation of moment. So with that, summation of moment at B sub 1. So the summation of moment at B sub 1 equal to 0. Therefore, the clockwise rotation is equal to the counterclockwise rotation. So if we will now apply moment at point B, therefore at B, this will be our reference point already. So if we will have the rotation of our resultant of this lateral earth pressure, so the rotation with respect to B is counterclockwise, while the unknown A with respect to point B, the rotation is clockwise. So for the clockwise first, that is A times the perpendicular lever arm, which is 1.83 meters, which is equal to the counterclockwise rotation. So our resultant, for the resultant, this is rectangular. Therefore, it is 29.586 times the total height, that is 2.74 meters. Then times, since it is rectangular, so half of its height. So 2.74 meters divided by 2. Thus, our value of A is 60.689 kilonewtons per meter. Since we have already the value of A, we can define B by means of summation of forces horizontal equal to 0. So to the right equal to the left. But let us just place at the left side of the equation our B1. So B1 is equal to the forces to the left. We have the resultant of our loading. And since we already considered A at the right side of the equation, so it turns out to be negative. Okay, so B sub 1 is equal to the resultant, 29.586 kilopascals times 2.74, the total height. So minus the predetermined A, so 60.689 kilonewtons per meter. And B sub 1 is equal to 20.377 kilonewtons per meter. So let us set aside our line loads A and B1. Let's consider section 2. So for section 2 now, so if we will now check our diagram and apply now our concentrated load, so the resultant load of our lateral earth pressure, so by means of inspection, we will just consider summation of forces horizontal equal to 0. Wherein, for our summation now, by inspection, B2 is equal to C1. And if we will substitute C1 as B2, we can determine already B2 as 27.071 kilonewtons per meter, and that is the value of C1 as well. Set aside these values of the line load for B2 and C1. And let's identify for the last section. So for the last section, to identify C2 and D. Okay, so we will apply now moment at C sub 2 equal to 0. So identifying now the rotation. So the rotation of our resultant is clockwise, while for our D, the rotation is counterclockwise. So if we will now assess the rotation now of our D is counterclockwise. So counterclockwise, that is D times 1.83 with respect to C is equal to clockwise. The resultant 29.586 kilopascals times 3.66 meters, the total height, then multiply with the lever arm, which is 3.66 divided by 2. And to identify D, D is 108.286 kilonewtons per meter. And by means of inspection, as you can see, D is related to the resultant already, which means that C2 is already 0. And verifying that, for our summation of forces horizontal equal to 0, to the right as C2, then equal to the left, and let's transpose already D. Okay, so C2 is equal to 29.586 times 3.66, our resultant, minus the predetermined D. And C2 is indeed equal to 0. So let's complete now our line load values. And let us already determine what is this strut load. So for the strut load is equal to the line load multiplied by the distributive length. So this is strut load, or in between strut loads, so we have now spacing which is equal to S. So for this line load now, the line load with respect to one strut load be multiplied to its distributive length. So the distribution now of this line load must be in between the strut loads. So we have already S all over 2 at the other side, and at the other is S all over 2 as well. So if we will combine the two, the total distributive length is equal to S. Starting with level A. So at level A line load times our distributive length, which is S. So A, that is 60.689 multiplied with S, that is 3.05. That is 185.101 kilonewtons. Next, at level B, for level B, we have two values of B. Therefore, we need to sum B1 and B2, then multiply it to this distributive length, that is S. So B1 is 20.377, so plus B2 27.071, so kilonewtons per meter, then multiply that to our distributive length S, 3.05 meters. Therefore, our strut load at level B is 144.719 kilonewtons. So at level C, so this level, we have 2 again, C1 and C2, multiply it with S. So our C1 is 27.071, while C2 is equal to 0. So multiply that with 3.05, the strut load is 82.568 kilonewtons. And finally, at level D, so at the strut load near the base, so D times S, so only one value of D, is equal to 108.286 kilonewtons per meter. Then multiply that with S, 3.05. The strut load therefore is 330.271 kilonewton. Okay, so for your practice problem, so the elevation and plan of a bracing system for an open cut in sand are shown in figure 1.75. Using PEX empirical pressure diagrams, determine the design strut loads given the unit weight of the sand as 16.5 kilonewtons per cubic meter, Phi prime as 30 degrees, X 1.8 meter, Z 0.8 meter, and the spacing S 2.5 meters. Okay, so that's it for braced cuts. Take care and God bless.